4.5 billion years ago, there was no Earth. There was only a cloud of gas and dust, and gravity deciding what it would become. Gravity is patient. It pulled dust into pebbles, pebbles into rocks, rocks into bodies, and those bodies into something that we would one day call home. This is the Earth before our Earth, a ball of molten rock. No air, no water, no peace, just heat and gravity and the slow work of becoming. There was no actual land, no seas, nothing was still, just a violent mass deciding if it would become a planet. This was not a peaceful birth. Our early solar system was a shooting gallery, and Earth wasn't finished being target practice. This is Our Planet Earth, Episode 1, Fire and Stone. This is what Earth looks like now, blue, alive, impossibly hospitable. But look back far enough and none of this was guaranteed. The question is not how life appeared. The question is how this planet survived long enough to even allow it. For hundreds of millions of years, Earth was hit, repeatedly, catastrophically, by objects large enough to melt the surface all over again. We know this because the evidence survived, written in ancient minerals that formed under conditions that no longer exist anywhere on Earth. These rocks are a record, not a complete one, but enough to reconstruct a story no one witnessed and no one could have survived. Every canyon wall is a library, every rock formation a chapter, and what they tell us is stranger than anything we could have imagined. In 1788, geologist James Hutton stood at Siccar Point in Scotland and understood something that changed science. The rock beneath him had taken so long to form, he called it no vestige of a beginning. In the 1860s, Lord Kelvin calculated Earth's age at between 20 and 400 million years. Brilliant, rigorous, and completely wrong. The discovery of radioactivity changed everything. Rocks decay at known rates. Those rates could be used as a clock. Suddenly, deep time had a number. Today, radiometric dating measures rock ages with extraordinary precision. Earth is 4,540,000,000 years old, give or take 50 million years. If Earth's history were one calendar year, humans appear at 11:59 p.m. on December 31st. We are the last few seconds of a very, very long story. The violence of Earth's early years is still written on the surface. Ancient craters, deformed rock, the scars of a formation no one was around to witness. Learning to read these walls took 2 centuries, and what they tell us about Earth's first billion years is stranger than anything we could have imagined. Every layer a chapter, every mineral a timestamp. The rock remembers everything the planet has been through, and we are just learning what questions to ask it. For a long time, we imagined early Earth gradually cooling, quietly settling toward habitability, a patient transition from hot to temperate. That picture is incorrect. The Hadean Eon, named for Hades, lasted 500 million years. It was not a gradual cooling. It was sustained planetary violence, and then it got worse. Roughly 4.5 billion years ago, a body the size of Mars was on a collision course with Earth. Scientists call it Theia. It was not going to miss. The impact almost vaporized both objects. The heat was enough to melt the entire planet again. A planet-scale explosion unfolding in slow motion. Earth was reset, melted to the core, and from the debris of that collision, something entirely new would form, something that would change everything. The moon is the evidence. Its surface is ancient and preserved in airless stillness, and its composition tells a story that points directly back to Earth. When Apollo astronauts returned moon rocks in 1969, scientists expected alien geology. What they found was a chemical match to Earth, the same oxygen isotope ratios, the same mineral signatures. The moon rocks showed almost no water, no volatile elements. The giant impact explains why. The heat boiled everything off and launched the dry remnants into orbit. Within roughly 100 million years, the debris coalesced into the moon, forming so close to Earth it would have appeared 16 times larger in the sky. The early moon generated tides 1,000 times stronger than today, stirring the young oceans with a force that may have driven the very chemistry of life. Between 4.1 and 3.8 billion years ago, the inner solar system experienced what we now call the Late Heavy Bombardment, a sustained campaign of impacts that resurfaced Earth and the Moon repeatedly. The Moon preserved the record. Earth's geological activity erased most of its craters. The Moon, being geologically dead, kept the count, and the count is staggering. The bombardment brought destruction, but it also may have brought the oceans. Comets and carbonaceous asteroids carry water locked in their structure. Billions of tons of impacts delivered that water to a cooling Earth. The first oceans formed roughly 4 billion years ago. They were not blue. They were hot, acidic, full of dissolved minerals, an alien chemistry that bore no resemblance to what we know today. Each impact was also a delivery. Water molecules locked inside incoming rock and ice, released on contact. The ocean built itself one catastrophe at a time. The early ocean floor was dominated by hydrothermal vents, cracks where superheated mineral water met cold ocean. Chemistry happened here at rates impossible on the surface above. The early ocean was a chemistry experiment at a planetary scale. Iron, sulfur, calcium, carbon dissolved together in conditions that no longer exist anywhere on Earth. There was no oxygen in the early atmosphere. The air was nitrogen, carbon dioxide, and methane. Breathe it today, and you would lose consciousness and die in seconds. In 1952, Stanley Miller and Harold Urey simulated early Earth's atmosphere in a flask and ran electrical sparks through it. Within a week, they had produced amino acids, life's building blocks, spontaneously. The leading candidate for life's starting point is RNA. Unlike DNA, it can both carry information and catalyze reactions. It may have been the first molecule capable of copying itself. Life may not have begun in a warm, sunlit pond. It may have begun in complete darkness, under crushing pressure in the chemical gradients of the deep ocean floor. The least welcoming address in the world. The oldest confirmed evidence of life is 3.7 billion years old. Stromatolites, structures built by microbial mats, found in ancient rocks in Greenland. Life was here before Earth was even 1 billion years old. The first life was impossibly simple, single cells without nuclei, without organelles, and yet they were alive, and they were already changing the world. Banded iron formations are the chemical fingerprint of the first oxygen-producing life. As cyanobacteria exhaled oxygen into the ocean, it reacted with iron and settled to the seafloor, layer by layer by layer. Beneath the ocean, a different engine was running. Plate tectonics, driven by heat from Earth's interior, was cycling carbon, building mountains, and maintaining the conditions that kept the planet habitable. The mid-ocean ridges form the longest mountain chain on Earth, 60,000 kilometers of volcanic seafloor spreading, almost entirely unknown, and one of the reasons Earth continued to live. Earth has a magnetic field generated by its liquid iron core. Without it, the solar wind would strip the atmosphere from the planet. Mars lost its magnetic field early, as well as its atmosphere. Earth's core is still liquid, still churning, still generating the field that protects every living thing on the surface. It has been doing this for 4 billion years. By 3.8 billion years ago, the worst was over. The crust was stabilizing, and in the shallow water at the edges of new rock, something impossible was beginning. The sun in Earth's early years was 20 to 30% less luminous than today. By every calculation, Earth should have been frozen solid for its first 2 billion years. The math says ice, the rocks say liquid water. Something does not add up, and this contradiction, the faint young sun paradox, remains unresolved today. Volcanism may have rescued the planet each time, pumping greenhouse gases into the atmosphere until the warming overwhelmed the ice. A planet that froze and thawed and froze again. Something kept early Earth warm when the math says it should have been frozen. We have hypotheses. We do not yet have certainty. And that uncertainty is not a footnote. It is the heart of the problem. The first 500 million years of Earth's history are almost entirely unrecoverable. The Hadean record was destroyed, recycled by plate tectonics, erased by bombardment, melted beyond recognition. Mars is what happens when the conditions don't hold. It lost its magnetic field, it lost its atmosphere, its water vanished. Earth threaded a needle that Mars missed, and we still don't fully understand why. We model what we cannot observe, we infer from what survives. Hadean Earth science is less like reading a document and more like reconstructing one from ash. The Jack Hill's zircon crystals of Western Australia are the oldest material on Earth, 4.4 billion years old. The fact that they survived at all borders on miraculous. One hypothesis says life began at the surface, in warm, shallow pools exposed to sunlight and lightning. Darwin himself imagined something like this in an 1871 letter. It remains a serious scientific position. The competing hypothesis places life's origin in deep ocean alkaline vents, in total darkness, driven by chemical energy gradients. No light required, no surface required, just chemistry and pressure. A third hypothesis, panspermia, suggests life's precursors may have arrived from elsewhere. The Murchison meteorite, which fell in Australia in 1969, contained amino acids and complex organic molecules from space. We do not know where life began. The evidence supports multiple hypotheses. The debate is active and unresolved. That is not a failure of science. That is science working exactly as it should. The universe is 13.8 billion years old. Earth is 4.5 billion. Life appeared less than a billion years after Earth formed. On the cosmic timeline, it happened almost immediately. Earth is not a large planet. Jupiter could fit 1,300 Earths inside it. We live on a pebble, a very precisely positioned pebble. If Earth's history were compressed into 1 meter of rock, all of human civilization would be a layer thinner than a coat of paint. We arrived at the very last moment. The Late Heavy Bombardment delivered impactors estimated to match the entire current mass of the asteroid belt, all arriving within a few 100 million years. The numbers are almost incomprehensible. We have confirmed over 5,500 exoplanets. Many orbit in habitable zones, but Earth's story suggests habitability requires far more than the right distance from a star. The James Webb Space Telescope is now analyzing the atmospheres of distant planets, searching for oxygen, methane, water vapor. We have not found them yet, but we are finally able to look. Every catastrophe was also a gift. The bombardment brought water. The giant impact created the moon. The moon stabilized Earth's tilt. Destruction has been our foundation. Everything on this planet, every tree, every ocean current, every breath of oxygen is downstream of that first billion years of violence. The catastrophes were the beginning. All of this, every organism, every ecosystem, every breath, traces its origin back to a planet that should not have survived its own formation, but somehow did. There is a moment geologists describe, hand flat on Precambrian stone, knowing what you are touching is older than the oxygen you are breathing. It changes something. We are drawn to rocks before we know why. It may be the oldest impulse we have, to hold the deep past in our hands and feel connected to something larger than ourselves. Discovery rarely feels like triumph. It feels like suddenly understanding something that was always there, as if the answer was waiting and you found the angle from which it became visible. This is where it started. In this kind of violence, in this kind of heat, everything that ever lived emerged from what you are looking at right now. A drop of water. 4.5 billion years of violence, chemistry, and chance reduced to its most essential product. This is what the solar system made, on this one rock, in this one corner of the galaxy. Seen from the moon, Earth is small, a blue circle in an ocean of black, and it is the only place in the known universe where any of this happened. There are 2 trillion galaxies in the observable universe. Each contains hundreds of billions of stars. The universe has run this experiment everywhere, on almost every available surface. And yet here, in this pool, on this planet, the chemistry worked. The impacts arrived. The magnetic field held. The moon formed at the right distance. Everything that had to go right, went right. And the water was still. For the first time in the planet's history, there was a surface that reflected the sky. A quiet ocean under a young, enormous moon. And something was about to happen inside it. And the universe had been waiting 4 billion years for the conditions to be right. We are made of this. The ocean is in us, in our blood chemistry, our cell structure, our evolutionary memory. We never left the water. We carry it with us everywhere we go. Life was not an accident. It was the most patient experiment in the history of the solar system, and it was just getting started. Thank you for spending this time with Earth's beginning. The story is far from over, and neither are we. If this left you with something, subscribe, leave a thought in the comments, or share it with someone who needs to know where they came from. Next episode of Our Planet Earth is The First Breath. From the first life to the moment, oxygen changed everything. We'll see you there.